it's all well and good, if you have the most aerodynamic car in the world, but if you don't have enough time to physically manufacture and get it ready to a competition standard, there's no point in doing it.
Milling a new car every time you want to test something.
It's both resource and time intensive, which we didn't have either.
A lot of teams like to show off their CFD testing. Overall, in the overall time performance of the car, it's only about a quarter of the actual how much performance it gains.
Running the car down the track, its behavior won't be perfectly predictable.
I mean, a question that's always come up in pretty much every single interview, it's why did you make this design?
Hello, and welcome to this episode of Off the Track. Today we're going to be looking at car testing, something that I think we've tried to do before in a limited capacity, but today we're going to try and make the all-inclusive guide to car testing. It probably won't be all-inclusive, but we'll get to that later. First, my name's Michael. I was part of Infinitude and Precision Racing, and joining me today is Fefe.
Hi, I'm Fefe. I was part of Ascension.
And we've also got Off the Track's own Ethan.
Hi.
Where are you from, Ethan?
I was in Ionic and Endeavour.
Cool. And we've got Aarav also.
Yeah, I was in Ionic and then Nebula as well.
And also joining us virtually, we've also got Alex.
Hi, I'm Alex, and I was part of Hydron.
Cool. The most recent experience there, and a world champion. It's great to have you on, Alex. So I think first we should really start by asking, why do we test cars? Because if you don't really understand why you're doing something, what's the point in doing it? I suppose, Fefe, do you want to start us off?
Yeah, I think testing is a critical part of your engineering development because of two major factors, and those being either validation or optimization of a car. I would say validation is a big part because you've spent all that engineering development time coming up with concepts, looking at theory to create a car, and you want to be able to support that with actual quantitative data. And then in terms of optimization, you want to be able to tweak minute little details of a car that you've based the theory on and get it to its best state.
Absolutely. Aarav or Alex, do you have anything to add?
Not really. That was pretty good, actually.
Okay. So there's some priority areas that we look at when you're allocating time to your testing. Things like CFD, FEA, manufacturing, the regulations, track testing. I suppose, Alex, do you want to give us a quick rundown on what you think each is best for, I suppose, what area of the car development?
Sure. So the most important thing in your car when you're making it is the regulations. That's where you get most of the points. The racing is just another area. If you lose all the points in your scrutineering, then you won't get any awards, you won't get any points. So in terms of the actual car, having it well manufactured to ensure that it meets the regulations is, of course, an important requirement. So, of course, testing just making sure you have the right quality control standards during manufacturing and whatnot. A lot of teams like to show off their CFD testing. That is certainly an important area for judging and for the car itself. But overall, in the overall time performance of the car, it's only about a quarter of the actual how much performance it gains. The most important area in terms of car performance would be its mass. If you have a light car, it will go fast. If you have a heavy car, it won't go fast, as there's limited energy source, the canisters that go into the race of the car. You'll have to conserve the energy as well as good as possible, basically. There's also some areas such as track testing that will validate results and also give you some areas of results that you perhaps couldn't do virtually, for example.
Yeah. And so looking at the scorecard, I found 5 areas of the design and engineering scorecard that relate directly or at least somewhat to testing of the car. Aarav, did you want to speak about that a bit?
Yeah, so I guess the 5 criteria, they pretty much go hand in hand. It's really hard to do one without the other. They should really integrate with your design and testing. They should really, your CFD, physical testing, whatever, there should really be one cohesive thing, and that should be, I guess, reflected in your your development and the way you present it in the portfolio. I guess the main really takeaway is it's really like whatever testing you do, right? It's how it affects your design development. So it's like, let's say you did like a wind tunnel test, right? That's great. Like we love to see it. But then actually, how did you use what information you got from that? And how did that like physically affect a change in your design? And how did it make it better, worse? Yeah, that's really kind of the main point.
I think it's also worth noting that just because this is an engineering area and we're looking at testing and design, it does not mean that it's not related to the project management. You know, that I suppose there might be a perception that project management is an enterprise thing because it's probably going to be done by someone on the enterprise side of the team, if your team's divided that way. But I think it's just as, if not more important, that the engineering have correct project management, because that's one of the areas that you're going to see, you know, hazards in terms of not only safety, in terms of physical safety, but also time blowouts and all those kind of things. Does anyone want to have a quick stab at that one?
Yeah, I'll have a stab.
Yeah.
Just to add on that, yeah, I would say project management is huge, and especially with respect to time. Ideally, as engineers, we would want to use the most accurate equipment available to produce the most accurate results, but unfortunately, we are restricted to a certain time frame. And because of that, it's also important to consider the overhead when performing tests, especially in the case of virtual tests. That's your turnaround time and how efficient the actual software is. So yes, it's very important to be able to reflect the actual performance of a car, but at the same time, you're limited to a certain amount of time, and you need to manage around that based on what you're trying to do with the tests.
I kind of adding on to that, like it's all well and good, you know, if you have the most aerodynamic car in the world, but if you don't have enough time to physically manufacture it and get it ready to a competition standard, there's no point in doing it.
Yeah, because it's not just sticking a block of foam in a CNC machine, hitting go, and then putting some wheels on it. There's a whole finishing process that goes into it, and that kind of stuff. So I suppose that's obviously something you need to take into consideration as well, correct?
Yeah.
So when it comes to your testing informing design, I suppose we talked about that. Do you want to talk about like the validation and comparison and kind of how best to validate results and that kind of process?
Okay. I can start.
Yeah.
If you want. So I guess you kind of have your two testings. You have your virtual and your physical.
Yep.
So I guess you can, once you get your virtual, the best way, you want to iteratively test your model. So what we did is every time we made a change, so first I guess we would develop your kind of your computational, your design and how your testing setup, and that would remain the same once we got that sorted. Throughout every single design we made, every change we made, and every time we made a change, we would go and check the results, to do like run the tests, see if it made it better or worse, and then really understand why. And on the other hand, the kind of your physical tests, we will take the changes we couldn't see kind of that wouldn't affect aero, such as like the launch angle or kind of your wheelbase, things like that. That's going to be separate tests. But I guess another point is kind of validating your physical tests or your virtual tests and seeing if they correlate with the physical results. So what we did, I guess, is we had a little modular car. It's very rudimentary, but we had 3, 4, 5, like, you know, different wing designs, different, front wing, side pods, different features of the car, and chucked them on this modular car, ran it down the track, and we say, did this kind of correlate with what we're seeing on the computer? And if yes, why? And if no, why not? And how can we improve our simulation to really see why, to kind of get them similar and be the same?
Yeah, I might just add on to that. Just talking about validation, I think a good way to break this down is if you have a sound understanding of something, let's say the aerodynamics, right? And you want to test a major concept or theory that you're putting on the car, maybe to the front wing or the rear wing. That's something that's important to validate through your CFD or physical testing to ensure that what you believe in the theory matches up with the actual quantitative results. And then in terms of comparison and optimization, you can reduce like the accuracy of a program and increase the efficiency to try to tweak that design and get the optimal version of that. For example, maybe you're trying to validate the positioning of a rear wing, whether it's connected to the actual canister housing or the rear pods. That would be something to validate through your CFD analysis. And then something like sweep angle maybe would be something that you would try to optimize.
There's a lot you need to do in both physical and virtual testing that neither by themselves can give you the best results. For example, virtual testing is good for testing single variables in a car design, such as aerodynamics, or you can theoretically calculate the friction of your wheel system. But we found that there's so many other variables that teams probably don't consider that goes into something like the wheel system. For example, the bearings, you can theoretically just use a friction coefficient and just calculate the friction of your wheels, but there's actually some oscillation in the bearing as it goes to higher revolutions per minute, and there's a lot of stuff that you have to physically test to understand what happens. So instead of like a linear curve in terms of friction, there's actually, we found more of a decreasing exponential in terms of the friction that you get from the amount of revolutions per minute in terms of your wheel speed. So yeah, totally make sure you do both physical and virtual testing to make sure you don't forget any of the important variables that go into the speed of your car.
I think there's far more depth there that you can go into, and that's something that I think teams need to keep in mind, is that this discussion might get really in-depth, but having an engineer or someone who's been in the competition before to collaborate with is probably the best way to get this kind of experience. So you've talked about a lot of methods here: CFD, physical testing. I suppose some people might be wanting a quick solution to testing. Are there any tests that just kind of test the overall car performance?
I haven't got overall car, but I can talk about like efficient estimations of things.
Well, first of all, is it reasonable to look for that kind of thing?
I think the only real measure of overall car performance you can do is a track run.
Yeah.
At the end of the day.
Yeah. And how comparable a track run's going to be between iterations? Because Aarav, you spoke about iterative design.
Unfortunately, the thing you have to consider with physical testing, and again, this is back to what Alex said, this is why it's important to do combination of both. Physical testing is subject to quite a lot of uncontrollable variables, which is what makes virtual testing more attractive. But in saying that, virtual testing, most software is limited in what it's able to account for in a car.
Yeah.
Just to give an example to what Fefe was saying, in terms of canisters, we made a rig that measured the thrust of the canisters in accordance to relative to time. So we found there to be, in terms of overall energy displacement, about a 20% difference between in terms of the canisters that we used. So between the top canister and the least energy dense canister, there was about 20% difference in terms of energy. So there's certainly variance in canisters that will impact the time of your car. But also, when the canister is punctured at the start gate, it never really punctures perfectly at center. So if it punctures to the side, your car will yaw. And of course, your car may not be perfectly balanced in terms of mass on either side. So your center of mass may be slightly to the left or slightly to the right of relative to your center line of your car. So your car is not a perfect straight down sort of thing that you test in CFD. It will yaw, and it will do some unpredictable stuff that you can't really test unless you do a proper track test.
Yeah, I mean, I guess like obviously like in terms of how much does aero really matter? Like obviously if you had a block and then you had, like an arrow, obviously the arrow would go faster, like hypothetically, right? Well, I mean, it will. But when you're looking at like kind of iterations that you have in your design, like if you're reducing 0.0001 newtons, that's realistically, you're not going to be able to see that at all. Because at that point, aero does not matter as much. I guess
I'll just counter that.
A little bit of controversy.
Heated debate. I completely agree. Aerodynamics is not the end all of engineering. However, I think when we come back to variables that are controllable and uncontrollable, aerodynamics is something that we can control to a significant degree in the car. Obviously, when it actually runs down the track, many factors such as humidity can affect the performance of a car. But if we can optimize the car to be in its best state, without all those conditions, then those other factors are uncontrollable variables that are simply out of our hands.
I agree with Fefe there. So, of course, it's you can easily make your car go 50 grams. That's everyone can theoretically have that capability of just making the car as light as possible to the regulations, having it fully legal and whatnot. So in terms of the variables that you can actually control that will affect the speed of your car, aerodynamics, although it won't affect it that much, maybe a few milliseconds. So we found 0.05 newtons of drag improvement accounts for about 20 milliseconds of car time, 20 milliseconds, car time improvement. So even though it's just, we're working on millisecond levels here, it could be what makes up the difference between first or, say, 7th place in terms of car times.
Okay, so if you're looking at a 20 millisecond change, what's the, I suppose, would it be anywhere near a standardized distribution? And if so, is there a sort of standard deviation from that would give you an idea of, how actually valuable that 20 milliseconds would be and how repeatable, I suppose?
I don't think there is, because again, there's so too many other factors that can affect the performance of a car at the same time.
Yeah.
And you can't possibly account for that. I guess you can do your statistics man yourself.
Yeah. A bit of a statistician. Yeah.
I guess you could do a statistical analysis on this, but I don't know how relevant that would be to the engineers in terms of what we can actually change.
Yeah.
In the car.
What would be quite interesting would be like having different kind of reductions in drag force or like your factors on CFD, and then having like a scale as into the benefits you will see on track time, like similar to I guess what you did, but kind of over a range of different reductions or different kind of forces, or like scale, kind of like a scaled version, if that makes sense.
Because my inkling with like a 20 millisecond reduction is it's measurable, but is it meaningful?
Yeah.
And I think that's something that testing really you need to think about is that you can be precise and you can be accurate, but just because you're precise and your results are accurate doesn't mean that you're actually getting the whole scale of things. Because if we look at Singapore, right, far higher humidity, usually hotter temperatures, so that means that you've got thicker air. Am I correct?
Yeah.
I don't know whether it's appreciably thicker, but anyway, if you're in the UK, the air can be a lot similar humidity, or it can be a lot drier, but it'll also be a lot colder as well. And so that's something that you can't really account for in testing. That's one of the physical track testing things you can't account for.
Yeah, even things like the altitude of a location, even though it's minor, does affect the density of the air.
Yeah, especially if you're going from somewhere like Mexico City to Singapore. Because Mexico City is quite high elevation. So when we're looking at, I suppose, common testing areas, we've talked about aerodynamics, we've talked about, to an extent, the balance of the car, the friction, and I suppose the reliability. I think we should just expand on these areas a bit more. So when it comes to aerodynamics, what are we looking to do? What are we looking to achieve, and how do we want to achieve that?
I think the two major things you want to be looking at in CFD are a visual analysis and a quantitative analysis.
Before we go any further, for the listeners who may not be familiar, what does CFD stand for?
Computational fluid dynamics.
And so what does that mean?
It's a virtual simulation of fluid dynamics flow. You can test airflow, other fluids like water. You can test an object in a boundary under certain boundary conditions and visualize how flow is affected by that object.
Okay, cool. Continue on with what you were saying.
Yes. So, in terms of the visual analysis aspect of it, things like looking at how the boundary layer is affected by the car.
Yep.
Again, those types of things I personally find in my time competing are less helpful for actual development of a car and more good for validating certain concepts, how flow separates around the wheels maybe, and looking at how the air actually behaves around different features that you want to introduce in the car. It doesn't really give you an informative result like quantitative analysis does. Like if you want to extrapolate a drag force, frontal area, things like that are much more useful, again, when you're rapid prototyping, making minor changes to front wing, rear wing, and different components to the car.
So just to be clear, boundary layer, you're talking about the body of the car?
The boundary layer is the airflow around the surface of a car before it goes into free stream air, which is just your normal airflow, basically, that's unaffected by an object.
I anecdotally have an interesting, I think, example of the visual analysis aspect of CFD, and that's what the German team at Worlds that I'm completely blanking, the German team that came forth, Sonic Boom, thank you, Peter. I don't know how I blanked on that, but anyway, Sonic Boom did testing and found that the low pressure zone behind the wheels, between the wheels and the AirPods, the side pods, were actually acting more like a solid body than with the airflow, and so they managed to incorporate that in their design. And so that's, I suppose, an example of where you couldn't quantify that low pressure zone in any real meaningful way, I don't think.
Generally, I kind of get what you're saying. Generally, separated flow, you can't really see quantitatively, but it does affect the pressure around the car and how air pressure is affected by that, which does have some contribution to the drag force. So you can still sort of get a quantitative measure of those sort of things. But yeah, I do kind of see what you're saying.
What I was trying to say is that if I was designing a car and I was looking at those results, it's the kind of thing you need to look at and to understand and to utilize compared to quantitative analysis. So you talked about quantitative analysis of drag force. You want to go a bit more into that, or I don't know, Aarav or Alex?
Kind of on a side note, really quickly, when I was talking about air behavior, the best way it was described to me is like, think about air being little, like it's a very sticky fluid. Think of it as like kind of ball bearings that are kind of dipped in honey. It's a weird analogy, but think about that kind of flowing over your body, your car, whatever object it is. The air really kind of want to sticks to that surface. The good way to kind of minimize your drag is to really have smooth kind of geometry and transitions between your different
I somewhat disagree with that, actually.
Really?
Because that was very helpful for me. So better come up with something better.
Generally, I would agree, especially towards the rear sections of a car. However, I think you'll find with most real vehicles, planes, cars, etc., the inclusion of objects like vortex generators. The point of that is vortices and turbulent flow have higher momentum than laminar flow. Now, they might cause generally an increase in drag, which is why you generally don't want that sort of thing. But at the same time, because they have higher momentum, they tend to separate less than laminar flow. So if you can encourage higher momentum vortices in areas that are experiencing a large wake behind them, then that might prove more beneficial than just having pure laminar flow.
Actually, thinking back, we did look at kind of, especially behind the wheels, on different features, like towards the side pods, and kind of around the wheels to kind of you kind of actually add vortices to kind of, as you were saying, increase momentum.
Okay.
Yeah.
The honey ball bearing thing. I liked that, but apparently it's not accurate. So make sense of what they talked about.
Generally, as it's a good rule of thumb to go by, but again, vortex generators are not beneficial for every circumstance. It's only if you're trying to really reduce the separation of flow.
I suppose it comes down to the mindset of CFD is a tool.
Yeah.
Track testing is a tool. FEA is a tool. All these things are tools. You need to know when to use them. I think that's probably the more important thing. If you can find someone to collaborate with that knows the nitty-gritty details of these things, you just need to know how and when to use the tools. Well, I suppose they'll know the detailed how. You need to have the general concept of how to use the tools, and then the application can be done with that collaborator. Yeah.
If I could add on vortex generators,
Absolutely.
it's maybe a thing that's used in professional industries, but on the scale of an F1 and school car, we're working at such small scales that any vortices that you try to generate, and especially after the car is manufactured, after you've had layers of paint on, you can't get the precision needed to ensure that your vortexes won't just go out of control and just create a larger wake region behind every bit of the car. So personally, I would not recommend trying vortex generators on a car.
That being said, maybe that's an innovation area. Maybe. I don't want to send people down the wrong path, though.
That's for them to test.
I would preface vortex generators by saying, even in professional industry, they use it for specific areas on the vehicle, and scale is a very significant part of that.
Because while, for us, it doesn't appear that the aerodynamics of this cup are much different from a much bigger cup, air molecules stay the same size. And so a much smaller car is going to... Never mind. Moving on.
Well,
can anyone tell that I'm not an engineer?
Well, yeah, that is true. But the main... we're staying on vortex generators now.
Yeah.
The main point is, even in saying that, the same thing applies to vortices and turbulent boundary layers. Even at smaller scales, they still have higher momentum than laminar flow.
Yeah.
But like Alex was saying, if you can't get it to a controllable state and it produces circulation that's too large and uncontrollable, it may be to the consequence of a car's performance.
Okay, cool. So moving on then, I suppose, what are some of the parameters that you look at, and I suppose some of the details you need to be aware of with CFD? Ethan or Alex, do you want to take a go at this one? Or we can go to our usual first suspect, Fefe.
Wow, okay. Feel targeted here. The parameters generally tend to be specific to what CFD package you're using, but the primary parameters, I would say, are your definitions of an inlet, walls, and symmetry. For an F1 car, let's say, obviously you want to define a velocity inlet where the airflow is coming into the region that you want to test. You want an outlet where the flow is naturally going to go out. You want to define the wall being the ground or the floor that the car is running on. And then the other faces of the boundary would be defined as a slip symmetry or free air region.
What's the first one you mentioned? Was it slip symmetry?
Velocity inlet was the first one?
No, just before.
Oh, slip symmetry?
Yeah, what's that?
That's just like an open boundary condition. So with a wall, you still have a boundary layer attached to it because it's still a surface. But when you're testing the car on the track, the sides around the car and the top of the car are going to be free stream air rather than walls. Okay,
lovely.
And if your CFD package allows it, certainly have rotating wheels because they can make a big difference, especially the front wheel. The Magnus effect that it causes can account for up to 50 or 60% even of the car's drag, just from the wheel spinning.
Yeah, a big source of turbulence, I believe, would be due to the rotating wheels. And another condition, this is getting very specific to certain CFD packages, You can also define a source of thrust coming out of a canister in ANSYS software, I believe, which is limited in other CFD packages.
Yeah, you can do it in SolidWorks as well if anyone is using that.
Okay. And so I suppose you kind of touched on it a bit there, Alex, but is that a difference between static and dynamic CFD testing? Am I using those terms correctly as well?
I am not sure.
When you're talking about the spinning wheels, because I know that Britannia Red, when we interviewed them, talked about how they were simulating the car with a moving ground beneath the car, moving wheels, which was different from when I experienced testing and analysis, which was done in the now retired Autodesk Flow Design, and everything was still. It was just the air moving.
The thing about CFD, it sort of, in CFD, if you simulate the air to be flowing at a certain velocity, that's simulating the same effect as if it's the car moving at a certain velocity through the air.
Okay.
But yes, in terms of the actual wheels moving, what you're simulating is just the car moving forward without any rotation of the wheels.
Right. Okay.
The front wheels and really they really change, especially your visual outputs to what you actually see, and then that, like, if teams can account for rotating wheels and a canister, you'll really kind of, I guess it will change the way you view your design development.
But I guess back to what we were saying before, the discrepancy that you get from those results may affect computation time. And again, you have to consider overhead and the amount of time that you have available to do this testing.
And so that's something that that's I suppose the optimization considerations. So I've got some in the doc here, some initialisms, RANs, LES, and DNS.
Yes.
What are those? Are they important? Why do we care about them?
They're just solver types.
Right. So what's a solver?
The solver is just how the CFD is like resolving the flow.
Right.
Something like direct numerical simulation is the top of the industry solver.
Yep.
It basically resolves every regime of flow. Turbulence, whether small eddies or large recirculation zones, are simulated by DNS. LES, large eddy simulation, just removes the smaller turbulent regions. And RANS, Reynolds average numerical simulation, it still simulates turbulent flow, but it simplifies it significantly compared to the other two. Obviously, DNS is the most accurate software that you can use. However, the computation time that it takes to do a direct simulation is so much more significant than RANs, which is what most CFD packages use, that for the purposes of this competition, it's far more useful to use a RAN solver.
Right. And so I suppose looking for programs to use, what would you guys recommend given your experience? I'll start with you, Alex.
Well, from what we've used, ANSYS, the ANSYS suite, so ANSYS Discovery and ANSYS Fluent, is definitely the most powerful in terms of what solvers they offer and the consistency that they can produce and the amount of control you have over the different variables that you put in. But if you have an Autodesk education license, you will have access to Autodesk CFD, which is plenty capable by itself. So I would definitely recommend you get one of those.
Okay. And Aarav, you spoke about SolidWorks.
Yeah, obviously ANSYS is kind of the best software for our purposes. But if you do have SolidWorks and you don't want to have you don't have time for the learning curve of ANSYS, SolidWorks, the flow design or the flow package it has inbuilt is very capable. The meshing settings are limited, but you can modify your walls, you can account for like your canister thrust and rotating wheels, moving wall. It does have a lot of features, but I guess you kind of need to understand and accept the limitations it has with meshing. But it is a good alternative.
Okay. Ethan, did you use any of those or did you use something different?
We did use Autodesk CFD throughout, but yeah, as I've said, SolidWorks is plenty capable, and of course ANSYS is probably one of the best out there for us to use at the moment.
Okay. What did you use, Fefe?
We used a combination of, or just CFD, ANSYS, AIM, and Flow Design, which is just a favorite of mine. Again,
Why a combination?
like we sort of discussed before,
Yeah.
for the major changes in design,
Right.
major design element changes, we would use a higher end simulation software
Right.
to see if there was a visible improvement in results.
Yeah.
However, when we're making minor changes to the car, maybe minor numerical changes,
Yeah.
like how long the side pod is,
Yeah.
maybe
Mhm.
we would use something with less overhead, more efficient, and that just allowed us to basically optimize those features.
Just another aspect of managing your time and resources. Okay, brilliant. Physical wind tunnel testing. Is that a valuable thing to do? I don't know. Did any of you guys do physical wind tunnel testing?
Nope.
No.
No? Alex?
We did, but only so we can show the judges, really.
Okay, all right.
Again, physical wind tunnels have a lot of assumptions that are associated with them.
Yeah.
And it also, like, let's say, open versus closed physical wind tunnels, that can significantly affect the quality of flow.
Yeah.
The grid that you allow airflow to enter through in an open wind tunnel can affect how turbulent or how laminar that flow is.
Right, yeah.
All these different effects, they're just more uncontrollable variables
than a actual CFD program. I suppose if you're going to go for uncontrollable, why not go for track testing?
That is the best. If you can, if you have the time, track testing.
I feel like most teams probably don't have access to a physical wind tunnel lying around.
I know that we had one at my high school. I also do not remember anyone ever using it, except on, I suppose, open nights when they showed the parents, because you can see it and it's really cool.
It's cool to look at.
Yeah, it's cool to look at. So if you want something to entertain yourself while you're waiting for your CFD to run, do that.
Hey, there's an idea. Set up a smoke tunnel in your pit display. Has anyone done that?
Oh, I have. I
think I might have seen it, but
I don't know how.
Not a bad idea.
Viable that would be.
Yeah, especially with the new packaging rules.
Yeah.
But anyway, obviously, the last couple of worlds, people haven't been able to repair their cars themselves, and they've had to just rely on shipping cars to F1 and hoping everything goes well. And so when breakages happened, and they did happen quite a bit, they couldn't repair them, and it's just not an ideal situation, I suppose. So FEA, which I believe is finite element analysis.
Yep.
Cool, I got one. How is that useful for, I suppose, assuring that your car's strong enough, that what you're using is correct? All those kind of things.
I did do FEA, but it was testing the wheels instead of the strength of the car.
Okay.
I will...
Why'd you do it on the wheels and not the car?
We did do it on the car, but I wasn't responsible for the car. I was responsible for designing the wheel system.
Yeah.
We could probably touch on that a bit later on the wheel systems.
Sure. Cool. Let's do that. Okay.
Right.
Now I'm down to my last two.
Okay,
All right.
FEAs.
Cool.
Okay, so you kind of want to figure out how much load you're putting onto the car.
Yeah.
And then tolerance above that's how include a factor of safety, like 1.5.
Yeah.
That's up to you guys to decide what that is.
Mm.
But you really want to look at the areas in particular that kind of are in contact with your deceleration system, whether you use the Denford one or use your own.
What do you think of the Denford system?
It depends on your car. For example, because it's got the two bristles that run kind of sideways. If it only hits the foam or the balsa, your body, then it's usually is quite good. But where we saw a problem is if it starts hitting 3D printed parts, especially with the new regulations for rear wings. I mean, they've been out for a few years now. There's pretty much no way, or there's not really a way to avoid that, and that's where the force from those brushes, because they are quite thick, they can break cars. And I think we see that almost every year. Every competition, we see cars braking.
The type of load that you experience is quite different as well. With the Denford deceleration system, you're experiencing a shearing force, and with a traditional deceleration system like a towel or maybe a wall, I don't know if anyone uses a wall, you're experiencing more of a normal force. So they're two different types of loads that are impacting the car.
So what's a normal force and what's a shearing force?
Normal force is head-on force, right on the object. Shearing force is a side-on.
A side-on, a force applied at an angle to something.
Parallel.
Parallel, but so if this is your wing, you're pushing against the wing.
Normal force, perpendicular.
Yep.
Shear force, parallel.
Along the thing. Cool.
This is certainly,
Alex.
Sorry. And certainly, it's not just, they're not always perfect, the stopping system, especially the Denford one. So our rear wing is completely above the bristles of the stopping system, but our rear wing still snapped off in one of our races.
Yeah.
And when we analysed the footage from the live stream, it turns out that it knocked our cars like sort of sideways on its side, and it ripped the ring off. So suddenly, there's some areas that you can't really account for, and I guess that was just unlucky on our part.
Right. Okay. So how can FEA help you with that?
FEA can kind of ensure, I guess, material properties are another thing, so you should include what material you're using in the FEA.
Yep.
But it's a way to kind of understand, will your wing, whatever feature it is, will it withstand the calculated load that puts on? So it's kind of just a way to reduce the risk of your car braking during races.
Okay. So what should you be aiming to achieve?
Like Aarav said, it depends a lot of times on the safety factor that you've applied.
Yep.
Generally in industry, it's about 1.5 to 2. But there's a bunch of different analysis you can look at with FEA. I think the most common that are relevant to F1 in schools is probably stress distribution and where the higher end stress is localized, especially if it's near like a bonded area or a weak point. That would suggest trying to reinforce that area structurally.
Yep.
And then safety factor will be dependent on your material properties, and that can inform whether your object can survive the ultimate tensile strength or yield strength that it needs to survive based on what the material can resist.
Kind of on the another kind of way to look at your kind of deceleration or your kind of your ending phase of the car is, look, we didn't look at this, but I know a few teams do look at kind of removable parts that are meant to break or like are meant to fall off, and that can be easily fixed. I guess that's up to you guys, or if you want to look into that, that is another way.
Like the magnetic front wings that Gary spoke about in previous World Finals. Yeah. Okay. And so, safety factor. What is the safety factor? Just plain like I'm 5.
So you can design something to meet its exact specifications, right? Let's say something needs to resist 150 newtons load. Yeah. But that does not accommodate the likelihood of something going wrong or other factors affecting that load.
Yeah.
So in industry, especially in aircraft, it's important to design above the base requirements, so that the design is safe.
Yeah.
Basically. And again, the actual safety factor is not it's not a definite thing. It's often assigned by industry. In this competition, there is no assignment of a safety factor. But again, generally, it's about 1.5 to 2.
Yeah.
Right. So when you say safety factor, you chucked out just an example of 150 Newton load. What are you trying to, I suppose, assess as the thing that you're applying a safety factor to? Is it, what you estimate the Newton force, the force to be at the end of the track? or is it on the number of runs a car will do, or
It can be applied to kind of all of it. So
all of it?
yeah,
Okay.
it's really up to the teams
Yeah.
and where they want to apply this safety factor.
Mhm.
It's a way of tolerancing.
Yeah.
Yeah, so it's up to the teams. So obviously, where you can, you would want to add it.
Mm.
Yeah, but I guess the one downside is if you go too extreme, you
Mhm.
start sacrificing on other
Performance.
factors,
Yeah.
and performance.
And that's, I mean, in an everyday setting, especially with aircraft, you see that fight between weight, I suppose cost as well, and the required strength of a part, and that's why we see carbon fiber fuselages and that kind of stuff happening now in aircraft.
Composite fuselages.
Composite
yes.
fuselages, yeah. So you're looking at the whole car and applying it down throughout. Okay.
Yeah.
So it's a holistic thing.
Yeah.
Okay. Cool. And so I suppose what are some of the limitations you experience with FEA?
I think the biggest limitation is FEA assumes a homogeneous, which is like a uniformly distributed distribution of material
It's all the same
when you're
throughout,
testing.
yeah.
It's the same composition
Yeah.
of that material, which is generally not the case when we produce our parts.
Yeah.
3D printing, especially with something like FDM, which is fused deposition modeling, which is your typical layer by layer 3D printer. It tends to produce voids, and because it's layer by layer, it produces objects with anisotropic properties, which means it's weaker in certain axes compared to others because of the generation of those voids. And those are things that can't really be factored in by FEA.
Right. Okay. I suppose when we look at the homogeneous distribution of material, I've thought up an example that you're probably not going to like, but sourdough bread, right? That's got lots of little air pockets and big air pockets, not very uniform. But if you eat a brownie, that's very dense and very uniform. It's very much the same. Is that a kind of a good way of understanding it?
I think that's a fine analogy.
Cool. I got one, guys. And so FDM, that's when you've got the nozzle and the filament. What about, I suppose, resin printing?
Resin printing is still technically
FDM because you're
layer by
merging the
layer.
layers,
It's not FDM. It's stereolithography. I
Yeah,
think
SLS.
is
SLS,
the
stereolithography, something, isn't it?
SLA.
SLA.
SLS is selective laser
Sintering.
sintering,
Yeah.
which is what you get your nylon out of. That actually, nylon, when you do SLS, produces quite a porous structure, which is similar to your sourdough example,
Really?
actually.
Okay.
Yeah. It's beneficial in that it gives self-lubricating properties, but again, the distribution of material is not perfectly even, which is not simulated by FEA.
Okay. Is SLA, so SLA is more uniform?
I believe so. It's finer,
Yeah.
but it's still technically a layer by layer printing.
Yeah, because you've got it moving up and the laser or the UV mask is exposing only certain parts.
But yes,
on
compared to a standard FDM printer, it would probably have less voids and more uniform distribution.
Good. Does it make it more ideal for F1 in schools, or is there other factors that affect that? This is probably more manufacturing. But
I would say yes.
Yeah.
If you can. And I think most professional 3D printing companies that teams collaborate with generally either select SLS or SLA solutions when printing. Typically, they just produce higher quality prints because they're professionally printed.
Yeah.
And again, structurally, something like SLA is probably more beneficial.
Okay.
And just to take note that the materials you can print on either types of SLS, SLA, and FDM are different. So generally, resins that you get from SLA we found were more brittle than the nylons from SLS.
Right.
So that's why we ended up mostly going with SLS, because we didn't want our wheels to shatter apart, which they did during testing.
Okay.
Nylon typically has higher ductility than most polymers.
Ductility is how brittle something is, right?
Ductility is the opposite of how brittle it is. It's how much it can deform without breaking, failing, basically.
So, like, if you think about a glow stick, I suppose, that's very ductile.
Yeah, a rubber band.
A rubber band, that's very ductile, yeah. Whereas something like, I don't know, a biscuit, that's not very, because you just can easily snap a biscuit.
I guess, yeah.
Yeah. I'm trying to break it down here for my my small brain to...
In saying that as well, material properties wise, I think stiffness, which is also not ductility, it's stress over strain.
So simple.
Stiffness is stress over strain.
Right.
That would be more important of a material property to have in something like your front wing.
Yeah.
And how much load it resists. Because you want it to resist a lot of stress without permanent deformation.
Right.
But like Alex was saying, something like a wheel system or that needs to engage in a lot of impact.
Yeah.
That can deform.
Yeah.
Would preferably have greater ductility.
Okay. All right. And I think based on how this conversation has gone, this is certainly an area that if teams are going to do FEA, they need to collaborate with an engineer or a past competitor. Yeah.
Especially like your manufacturer for your parts, what materials they offer, what printing technologies they offer, and kind of you have to really work with your manufacturer, I would say.
Yeah. And that's part of the whole design for manufacture life cycle, or flow, I suppose you could say. But anyway, physical racing, we've touched on a couple times before. I know, Aarav, you spoke about your modular car system a little bit. What was the thinking behind the modular car system? You said testing different wings?
It was different wings, different side pods, different rear pods, kind of your main features of the car.
Okay. So what made it modular?
The way it was modular, it was a one car body with different 3D printed attachments.
Oh.
That we could we essentially stuck on, and then we could remove after you've done the test and easily put on another car. While it's not perfect, we had limited time in the lead up for a competition. There was a rudimentary way to test or to get some correlation to see if there was a correlation between our virtual and physical testing.
So you were easily and quickly able to verify what you were seeing in CFD.
Yes. Yeah.
Yeah, because I suppose milling a new car every time you want to test something,
it's both resource and time intensive, which we didn't have either.
Yeah. Okay. Amazing. And so accelerometers, I know that Cold Fusion, and this is going back 10 years now, Cold Fusion used them in their testing and didn't find them too useful. Has it come a long way since then, or did any of you guys use accelerometers?
We both used it.
Yeah.
Do you want to touch on that?
Yeah. So unfortunately, we didn't we touched on it briefly whilst competing, but we didn't have a full understanding of it back then, so we didn't use it too much.
Yeah.
I think the main point of accelerometers, if you can have a 3-axis accelerometer and run it down a track, it's a good way to sort of look at how the motion of a car behaves when it's running a race, basically.
Right.
And I think you'll find with most accelerometer results, it's not a perfectly linear result in any direction.
It's not a straight line.
What we kind of did get from that data, we kind of got a graph that was almost like it was kind of like a stretched out parabola, kind of like almost like an inverse bathtub, if you can picture that. So what we got kind of our different stages of the race, like our you get your when the canister was punctured, your initial thrust, and your deceleration. What we really used it for was to find the max velocity, and that's and we could use on our CFD and kind of the velocity and the acceleration on impact with the deceleration system, then feed back into the FEA testing.
Right.
What I do know that kind of the next level, what teams have done, is then use that data to create kind of like they're called rocket simulations or 2D rocket simulations to kind of figure out a way to estimate your track time depending on your CFD results and kind of to estimate or predict what your car time will be. But adding on to that, what they have found that they're usually not very accurate, and it's more for the portfolio and to tell judges, look, this is what we've done.
Yeah. Why isn't it accurate?
There's too many variables.
Yeah. Okay. Comes back down to just physically testing a car, running it down a track. There's so many variables that will affect its performance and in turn the accelerometer's results.
Right.
Just on what Aarav mentioned about the model, one of our major things we did for engineering was making a mathematical model for our car, and we did try to include as many variables as we humanly can in that. I think it took us 2 months to compile just the maths behind the variables. So we had the resolving forces from the Tedline guide, from the aerodynamics, from how it resolves. There's a moment on there when the center of pressure is behind the center of mass, and the friction and how the friction resolves the yaw, and of course drag, thrust from the canister and whatnot. But at the end of the day, it was pretty accurate to our track times. We were only off by a few milliseconds in the end, I think.
Oh, wow.
But I think that was more of luck. That was more a factor of luck
than
actual skill.
No, just take the win.
In the end, I would still recommend teams do track testing, physical track testing. And in terms of accelerometers, in case you can't get your hands on one, you can use slow motion testing and put stickers on your car, tracking stickers, and just track those stickers in a software such as Vernier Logger Pro and gather graphs from that. Although you do, speaking from experience, need more than 240 frames per second in your high-speed camera.
That's something else that's in favor of physically testing, actually. It's obviously a dynamic case when you're running the car down the track. Its behavior won't be perfectly predictable. And when you're testing something in CFD, you have to sort of assume that it will be behaving in this constant manner, which is simply not the case.
So I suppose I'm actually quite interested because applied maths and mathematical modeling is kind of my bag. So what kind of model did you use? Is this differential equations or?
It was very much I guess your Suvat equations, your very basic, kind of projectile motion equations. And then it was iterating over. So I think the accelerator was to 10,000. It was to 100th or 1,000th of a second, and then it was just kind of iterating each second over to kind of generate. It was years ago, and we couldn't get it to work. I think Alex might know more about it because yours did work.
Ours is. In the end, the maths was high school level maths, but there was just so many variables in the thing that we made, the race model. So of course, in terms of the resolving moment of the Tedline guide, you have the 20 Newton force from the weight at the end of the track, and that you just use trigonometry to calculate how much it's displaced from the Tedline, from the center line. And that's, you get your resolving forces from there, and then from there you can derive the moment and whatnot. And in the end, it was just done in 1 millisecond increments, and we just used Suvat for each of the axes of movement. And we just essentially just kept incrementing in 1 millisecond increments until we got the race time and until we got graphs that we could accurately use.
Right. So you're taking a statistical approach to your model in a way because you collected all this data.
Somewhat. There was certainly physical data that we used that we put into the race model, such as our wheel testing rig, which measured the acceleration of the wheel from the bearings, and we chucked that into the race model.
Okay, cool. I know from previous experience and seeing some portfolios that not doing track testing has been put down to some teams is because they don't have a track.
I didn't have a track. Our school didn't have a track.
Okay.
Both world final campaigns or lead ups, we never had a track. While a track is ideal, it adds kind of more another variable that you can emulate and simulate your actual race. You can still do that is an excuse to not do track testing, period. like what we did, we used the floor. We measured 20 meters. It's adding more. It's not adding more variables, but it's better than not doing it. So what we did, we had the floor, had the 20 meters. Someone would hold the tether, the string on the other side. So again, it's not the 20 newtons that that's in race condition, but we were still able to consistently run the cars and generate data that we could analyze. And the way we kind of reduced errors or kind of minimized the systematic error was running the kind of cars for more laps. Kind of the point I'm getting is, as long as it's consistent and you do enough runs, you will still be able to generate kind of some data that you can analyze and extrapolate.
And now that you've mentioned systematic variables, I suppose this is something that I did in year 8 and 9, 10 science, and later in my physics as well in high school. So if you want to talk about variable control and that kind of thing, I suppose your science teacher, if you don't have a collaborator, would also be a great place to start. But do you want to just have a quick rundown of random versus systematic?
Okay, so systematic errors is something that's exactly the same between each run. So they won't affect the trends you see in your data, whereas random variables are things you can't control.
They will affect the trends, but they will affect it in the same way every time.
Yeah.
Yeah.
I guess, a way to look at track testing actually is to think about the physics or chemistry or science reports you do at school and take each kind of test that you do for a different system and kind of think of it as that way. Look at your aim, your results and your discussion. Really kind of think about it that way. I think that would help you, especially when it comes to portfolio writing, as a clear way to understand and talk about your testing.
And I think from memory, the engineering document supplement we had for Infinitude was a lot of that kind of stuff that we documented over the period. Though, don't quote me on that because I had nothing to do with the engineering in Infinitude. I just seem to remember that. But yeah, so you're testing your car a lot on the track, or maybe you don't have a track on the floor, which it seems no excuse, right? You can just use the floor. Everyone has a floor, right?
Yeah. So in our school, we do have a track, but we end up we only really take it out for open days and expos.
Yeah.
When we're actually testing the car, the times that we did, we always just use the floor because it was so much faster to set up. It really just you just need the testing to be consistent in terms of what you're putting in every time. And if you're using a track or if you're using a floor, if you're running the car multiple times, the floor is plenty adequate for testing a car.
So if Hydron world champions can win the competition using the floor instead of a track, I don't think it's much of an excuse. But that being said, obviously you're testing the cars again and again. Is there some kind of fatigue on the cars in this process?
Yeah. In industry, what you're looking at is called the bathtub curve, kind of a prediction of a system's life. So it's kind of best way to describe it is at the start of a new system, its failure kind of rate is very high because it's untested. So as you test it more, it decreases and flattens out for a period of time. Then towards the end of the system's life, it picks up again because parts are wearing out, there's fatigue, and all that. Okay. So what you really want to look at in your races is see how many races your car has to do, your design life of the car, which I believe is it 8, 12?
We looked at this earlier, and so you do 8 runs in a competition, like between your automatic and your reaction racing and all that, but with A and B cars.
Yeah.
So 4 runs, I think. 4 runs for each car. Yes? No? Because it's A in lane 1, B in lane 2 or whatever, and then the other way around.
But that's not inclusive of extra runs that the car might also need to.
Exactly. So you I suppose that is the theoretical. That's what you'll need to do, but I suppose it's a safety factor.
Yeah, exactly.
You'll need to do more, and if you get into knockouts, that's a further 4 per car.
Yeah.
If you are going to win anyway.
Just expanding on the property of fatigue, like we were saying, the car's going to have multiple runs, and because of that, it's going to have a semi-constant load put on the car, and because of that, if we go back to something like FEA, we can only really test it for a single load case. It can't really accommodate things like fatigue and fracture, and that's where things like physical testing are very useful in terms of structurally testing the car.
You have anything else to add?
No, not really.
No.
Yeah.
Cool. All right. Ethan, Alex, you guys got any wisdom?
I think we're good there.
Cool. Amazing. I know some of the things that have been done, and a lot of the top teams have done this, is measuring the canister discharge, and also, I suppose, the amount of gas in a canister. Can you guys talk about that? I know, Alex, you mentioned like a 20% variability in canisters?
Yeah, it was something close to that.
Yeah.
But when you're track testing, you should try to measure how much gas your canister is discharging every time. So we found anywhere between, in the canisters that we use, like 6 point something grams to 7 or 8 grams of gas that gets discharged every time. So measure that every time you do a run down the track. Put in the same spreadsheet that you have, and have a system for compensating for it. I know this is certainly one area we didn't do enough of. If you do enough track testing, you can probably do some statistical analysis to show how much the gas of the canister affects the performance of the car and whatnot, and you can probably compensate for it, but that's up to another team to figure out.
Yeah.
Another thing to look at would be where the puncture is on the canister, because there is a lot of variability. I think, as I think Alex mentioned earlier. So you can have a look, and if there's any extremes, discard those results. Just a way to make your data more accurate, or your trends.
Yeah.
I think the puncture of the canister presents a lot of the uncontrollable variables that we were talking about earlier. And if you can compensate for it, that would be a major benefit to increasing the accuracy of physical testing.
Right. And so I know that I've seen previously teams look at the launch of a car and trying to engineer their car so that the canister forces the car to I suppose, move in a straight line along the center of thrust. I think I'm talking about the tipping moment. I believe they term it, when your car tips that way or that way when the canister's punctured. Is the randomness of that canister puncture going to make any efforts to alleviate that pointless, or is it something to consider?
We found it was something to consider. I know teams look at, and we did as well, canister depth and canister angle. Because you can, I think it's 3 degrees still, or 2 degrees, 3 degrees that you can actually change, and just things like that, especially and center of mass as well of the car. All these factors, I guess, will help you reduce that tipping moment.
Okay, and I suppose we'll leave the proof to that to the reader, or I suppose in this case the listener or viewer. So Alex, earlier you mentioned wheel systems and how you use FEA in the wheel systems. I think let's take a step back and look at the wheel system as a whole. How or what are you aiming to achieve when you're looking at a wheel system?
Right. So within the wheel itself, you're looking at to have the minimal rotating mass that you possibly can to reduce the moment of inertia. So of course, the less if you have a heavier wheel and you need more energy to spin it up, that's energy that's coming from the speed of the car into spinning up the wheel, essentially. So you want to have the lightest wheel possible, but you also don't want it to break every time. So I guess that's where FEA comes in designing your spokes and the thickness of your wheel systems, wheel areas to be adequate to survive the races of the car. Within the wheel system itself, you need a support system that could support the wheel, but it also needs to be rigid. So if your wheel flexes all over the place because you have a flexible wheel system, that's also energy that's from the track that could potentially be going into the speed of your car that's being dissipated into other forms of motion and also heat. So certainly having the rigid and aligned wheels and having the lowest rotational mass possible.
Okay. I suppose I've also had a lot of teams document that they're using alignment jigs, and I know that bearings are a big deal in wheel systems. What I suppose does a testing perspective play when you're looking at the performance of bearings, the performance of the alignment of a wheel system?
I'll just speak for the wheel itself. In terms of minimizing mass, it's a fairly simple thing that you can test. If you have a CAD model of your wheel, it's easy enough to go into the CAD properties to determine the rotational inertia of whatever wheel iteration you're working on.
Okay. Alex?
Yeah, well, we did a lot of testing in bearings and also the wheel itself. In terms of the wheel itself, we found the main limitation wasn't actually how thin we can get it without breaking and whatnot. It was the manufacturing of the wheel. So we end up using CNC turned PEEK wheels. And the wall thickness that we end up using on the outside ended up just being the thinnest that our manufacturing source can make it down to, which was pretty reasonable at the time. But after we went to Worlds, we found that the other teams had wheels at like a third of the weight of ours, and we thought we did pretty well, so we're like shocked. But they were from Germany, so Sonic Boom, kudos to you. But
they did a lot of research on their wheels. I've seen their research on their wheels, and I'm just blown away. Like jigs and injection molding, and it was crazy. Yeah.
From looking at it, like we had machined wheels and they had injection molded wheels, and we were just shocked when we touched them. They were so rigid and they were so light. But also another important thing in your car is bearings. So you want the lowest friction possible in the bearings. So the reason you're using bearings in the first place is to not increase to reduce the friction of the wheels and allow them to spin for longer, essentially. Allow them to spin up faster. I know there's some debate going around on whether you should have your wheels slip or if they should spin up to speed. Because if your wheels slip, it doesn't matter if they're slipping a lot or if they're slipping just a little. You still have the same friction force coming out of it. But from our perspective, we just tried to get the lowest friction bearings possible, and we use the rig to spin them up and time their decrease in velocity.
Okay. So when it comes to bearings, what's a good bearing?
I guess we did do some testing on the bearings. There's three kind of types. You got this is from memory. This is kind of more Ruben, who was the other engineer's kind of side of it. It was steel, hybrid, and full ceramic.
Okay. And
you have three types, and I guess we tested them, and I think we did find that full ceramics were the most efficient. We basically just spun a wheel and with a Dremel and saw how long they spun for.
Right.
A simple test for that. But I guess
is that a realistic speed for an F1 Schools wheel?
No. But it was a way that we could get it consistent between each test.
Okay. What would a realistic speed be? Do we have any numbers on that, or
about 14,000 revolutions a minute?
Okay.
Minute or rad?
Per minute, sorry, RPM.
14,000 RPM. Yeah. Okay.
It depends on the diameter of the wheel, of course. With the large diameter wheels, it's spinning a bit less.
You can't really do anything manually to test that. You'd have to set up a whole rig to be able to test something at that speed.
Why do you need to set up a rig?
Because 14,000 RPM is unreasonable to spin by hand.
Okay.
We had a rig that got up to 12,000 RPM, and it had a sort of like a motor that went into the wheel, and then when it was done spinning it, there was a servo that disconnected the motor from the wheel. And we also had a photodiode opposing a laser diode, essentially laser tripwire that counted every time the spoke of the wheel passes. And from there, we can get a graph of the decreasing angular velocity of the wheel relative to time.
Right.
And from there, we can also derive friction and whatnot that goes into our race model.
Right. Okay. That's a very interesting way of doing that. And so I suppose going back to my original question, did you, between the steel, hybrid, and full ceramic bearings, did you test all three in that system, or?
We did test steel and ceramic hybrids, which are ceramic bowls in steel races.
Right.
We never tested full ceramics because of they are very brittle, so we don't want them to break. So we just ignored. Well, not in our latest testing rig, anyways. But in the latest testing rig, we only tested steel and ceramic hybrid. Another area that is worth testing is how you handle your bearings and how you lubricate them. So the lubricant from the factory, and also removing the lubricant using isopropyl alcohol by soaking it in various amount of time. We tested 24 hours and 1 minute soaks in isopropyl alcohol. In the end, in this particular bearing that we used for our world finals, we just used the factory lubricant. It wasn't the fastest, but this also goes into the second point that I'm making, which is how you handle your bearings. Because as soon as dust, any amount of dust gets in your bearing, they degrade in terms of performance massively. So even though the factory lubricant wasn't the best, soaking it in isopropyl alcohol, which we found was the best, had us remove the seals from the bearings.
Right.
And that would just get way too much dust in the bearings, especially during shipping and during handling in our not that clean D&T lab.
Yeah.
They would just be bad by the end, so we ended up just leaving the seals intact and just using the factory lubricant.
Okay. All right. And so hybrid or steel, which one did you find to be better? Or should we leave that as a proof to the reader?
I think we'll leave that to the listener.
Yeah, I always hate when they do that in maths textbooks to me, but you know what? I feel like it's a valuable thing for teams to test that themselves. So, I don't know, have we covered most of the areas of testing that you think are important?
Yeah.
Yeah?
I feel, yeah.
When it comes to, I suppose, testing moving into design, what are the considerations? I think we've talked about a few of the things like, optimization and that kind of thing, but what are where's the interplay there between your testing and your design?
Because reliability is a big one.
In what way?
Okay, let's say you have the most aerodynamic car in the world, or the most aerodynamic wing. If it breaks, it's useless.
Yeah.
There's no way around it.
Okay.
I guess another thing is the regulations. If you can't manufacture it to be within, with your regulations, and let's say you get a proportional penalty, that means you can't, qualify for knockouts. You can't, you can't place the podium. Kind of has a lot of factors. So, yeah, those are the two big ones.
Yeah,
I would probably say, testing is a good way to be able to speed through the engineering design process. If you have a sound understanding of aerodynamics, you can generally just brute force the rapid prototyping process, making changes, testing it to see if there's an improvement, then moving forward, if there's an improvement, going with that design, if there's not, going with a previous design or another variable design. And it just allows teams to be able to really quickly work through that process.
Okay. And so you're saying that it's really important that you manage your time correctly.
Yep.
In that sense. That's one of the key areas.
I will add to that. Yeah. Again, you want a sound understanding of aerodynamics when you're doing this.
So would it be efficient for you to maybe not begin by designing a car, or maybe by designing a car, but designing it so that you can understand the aerodynamics and collaborating with people at the beginning to get that solid foundation of aerodynamics so that you can go into the design process and not be trying to figure things out as you go?
Yes, and that will dramatically reduce the amount of time that you have to spend otherwise researching topics.
Okay.
And generally speaking, self-research compared to speaking with a professional in the industry or a university professor, that's going to benefit you more in the long run.
Yeah, and I suppose that goes down to the initiation phase of project management. And so if there's any project managers listening at this point in the podcast, definitely consider that. But for all the engineers, that's something that you need to be talking to your project manager about. Aarav, do you?
Yeah, I agree completely.
Yeah,
that it's really important how you schedule engineering. Make sure you have enough time for each. I guess part of it. I mean, a question that's always come up in pretty much every single interview I've been in, during the competition, and now that I ask teams what I'm judging, is it's why did you make this design? Where did you get this idea from? Whether it's things I've seen in industry, or like examples online, and then they can validate their reasoning or whether it's something that they've thought of from their kind of aerodynamic knowledge. That always comes off, and you should always kind of have a way to justify your design.
Yes. And from our previous episodes, if anyone's listened to them with David Powell-Freeman, if you don't have a real and good reason that justifies what you're doing, the judges will know. Don't worry about how they'll know. They will know. And so are there any other aspects of car design, I suppose? I spoke earlier offhandedly about design for manufacture. How does the testing play into that design to manufacture type?
I'll give you an example, actually. From our personal experience. Minimum thickness of the material that you're milling. That often depends on the actual feature that you're constructing. But that's something important to consider and to test for, to see what the limits are in terms of how thin you can get maybe a skirt or something like that.
What do you mean by a skirt? I'm assuming you're not talking about the clothing here.
Like around the car, if you have a closed sort of car geometry, you've got the main base of the car, and then you've got obviously side walls around the car.
Another big thing is fillets, because most teams use a ball nose, I think, to mill the car, and especially kind of with 3D printed componentry that they have, like if you have kind of a rounded object and you put a square 3D printed part, they're not going to fit. So you really kind of want to make sure the fillets match up.
You can test those things generally in most CAD packages.
It's more of a
CAD
thing than testing it.
Like I know Fusion 360, you can perform an accessibility analysis to see like if you've only got access to a 3-axis mill, that can help you determine what features can actually be milled in a certain axis.
Right. Okay. And is there an alternative to a ball nose router bit, or is that just what we use because it does basically everything?
Just generally
you do get other
generally good.
Okay. That's just too much detail. Just figure it out in the CAD. Yeah. Cool. Now I know I don't know whether most countries do it now. I know that for Worlds we use foam blocks, but when you are looking at the national competition in Australia and maybe in other countries, it's balsa still. Is it worth testing the weight of your balsa?
Yes.
And I suppose also the foam as well.
The foam is kind of easier because it's a standard weight between all the blocks.
Is it a standard weight?
Yes, there's very minor discrepancy. They're like the older blocks, I think, pre the Singapore World Finals, there's a different weight.
So I remember that there was actually variation.
Yeah, but with like kind of back in the day, but the newer ones, it's less so.
Okay.
But I guess the main thing is, especially with the balsa, is you want to figure out how much your componentry weighs, and then how much kind of you're giving to your surface finishing, really smooth out the car and your geometry. And then for balsa, then you want to figure out what weight of balsa you want to use. Kind of work backwards in that way.
What determines that?
The weights of the other componentry.
Okay.
Just on that, I think another good thing to test, if you're able to test, is how the material, either foam or balsa, reacts to the type of bonding that you're using. Like, I don't know, Zap-A-Gap or some other brand of super glue.
Okay.
How that reacts to the material.
Okay. Epoxy, would that be a good bonding agent or?
Bit dense, maybe.
Bit dense. Okay. I don't know. I see them use a lot of epoxy in woodworking, which really shows you what my expertise is in. Things about this big, not this big.
Actually, I don't know how relevant this is, but apparently there is a shortage of balsa wood, and they're replacing it with a more high-density wood alternative. I don't know how that's going to affect.
Balsa's a softwood. There's been a massive shortage of softwood.
Balsa's hardwood.
What? Balsa's a hardwood?
Hang on.
Let's double check the facts here.
Research time. No, I think I've heard somewhere. It's a hardwood with softwood
Yeah.
material
Oh,
properties,
okay.
right?
It's hard because it's determined by like if you have pines on your trees or leaves.
Yeah. Yeah, it's really
generally balsa is like 0.1 to 0.14 grams per centimeter cubed from memory, which is very low density material. And I think the wood that they're trying to replace it with is Paulina, and that's about 0.4 to 0.5 grams per centimeter cubed. So
wow, that's like
don't know how that's going to affect the competition, but that would be a significant increase.
I think
in density.
I can imagine how it would affect the competition, and that would be significantly heavier cars. Yeah, I don't know. Maybe pocketing out your side pods can help and things like
I know
that.
previous teams. I can't remember the name. It was in the World Finals that Horizon was in.
Didn't Horizon do it?
Maybe they
themselves?
left their underbody
Most teams
Is
do
it
that,
a
right?
common? Might be it.
Unfinished
they leave the
or
under.
We certainly did.
that wasn't
That was-
Horizon then.
It was one of the other Australian teams. I
Mm.
can't remember the name. Yeah, I think even like Hyperdrive left their front wings unfinished.
Oh,
I'm not sure if it was a weight saving thing. I'm really not sure, but yeah, there's ways to save weight where you can, because you want the car to be 50 grams.
Okay. And I suppose the last thing, and something I'll probably have to do on this episode, is quality assurance. How do you do like test for quality assurance? I suppose that's probably a big question. But
I think the biggest aid in that is going back to your point before, getting a mentor or an expert in the field to look over the work that you've done.
Okay.
Now, keep in mind, they've got their lives of their own.
Yep.
They're not available 100% of the time.
Yeah.
But if you can write up maybe an abstract or a summary of the results or major testings that you've done, send it through to them and get them to cross-check them, that will be of help to you.
Okay.
I guess more from a scrutineering side, creating like different jigs or like different running gauges, definitely help. I guess always compare, especially calipers are a big tool. Compare what you're manufacturing to your tech drawings, and compare that. See if it's within regulation. That's kind of the best way.
Okay. I remember from my first Worlds, in the engineering interview, they asked us, how did you make sure that your car was the same as what it was in CAD? Did you measure it with verniers? Did you measure it with lasers? I mean, my team wasn't the best, so I think we just used verniers, and they were a bit disappointed we didn't use lasers. Should you use laser
Interesting
beams?
critique.
Yeah, I thought it was at the time as well, but I don't know. What do you guys think of laser beams?
I think they're quite
Yeah, I
unnecessary.
think-
Yeah.
Honestly, for the effort to get hold of that technology.
Do you think, Ethan? Do you think gauges are a much better way?
Yeah, especially with
What do you?
You could manufacture the car,
Mhm.
get it 3D scanned, derive the CAD model from that,
Yeah,
and then measure it again.
measure it again
in
Yeah.
CAD.
I think that's what the judges at My Worlds were alluring to.
I don't see necessarily the benefit of that, considering the effort that
But
goes
as long
into
as
that.
you
Well,
tolerate
neither did I.
your
available.
critical or your rule breaking dimensions enough,
Mm.
and you should be fine.
Okay.
As long as you meet those critical regulations,
Mhm.
that's the key thing.
Do we only care about regulation meeting, or do we care that it's gonna do what we thought it would do?
Again, the major thing it affects is aerodynamics, and that comes back down to how much do
Does
the
it affect-
aerodynamics
yeah.
affect performance of a car. And with this in particular,
Mm.
this is a subset of aerodynamics.
Mm.
So how does that affect the overall performance of a car?
Right.
It's probably such a negligible difference
Okay.
that it's not worth it.
That
I
being-
think the critical thing,
Yeah.
like we discussed, is getting the regulations right.
Okay. And that being said, I remember, and Jesse might kill me for telling this story, but it's not really a story, it's an anecdote. But I remember that the Infinitude wheel system, when you're trying to assemble it, it was challenging. Say that. There was glue and there were bearings, and bad things happened. So I suppose that was a failure to design for easy assembly. But do you want to be testing your wheel systems, and how best would it be to test your wheel systems once you've got that car physically made in front of you?
That's a tough question.
Is it?
is.
No, I think just trying to get them aligned.
Yeah.
I feel that's an issue of project management again, though.
Yeah.
Because most teams, I feel like you've got the final product
Mm-hmm.
completed very close to the actual competition
Yeah.
date, and you don't get much of an opportunity to actually test in between.
Yeah.
If you plan for that,
Mm-hmm.
then by all means, the more testing, the better, really. But it comes down to
You need to be aware of scope creep. You need to make sure that your timeline is set.
how you're managing your time. Yeah.
And engineering is, I suppose, the biggest risk in a project when it comes down to the amount of time you can sink into certain aspects and the amount of time that you can lose to problems. Am I somewhere close to the money there?
Hit the nail on the head there.
Nail on the head? Great. Lovely.
So certainly there's a joke that the engineer in the team just goes, please just one more CFD test and whatnot. And then the manufacturing engineer's just in the back crying because he has like 2 less days to make a car.
I can neither confirm nor deny whether I've seen that at every single competition I was involved with.
The trick is just to have your manufacturing engineer be very aggressive to your engineer and just slap him whenever he tries to pull one of those.
Off the track does not officially condone physical violence, okay?
Hypothetically.
Yeah.
In a video game.
In Minecraft. Yeah. Okay. Did we have anything else to add with testing?
Oh, actually, I'll just add on to the quality assurance thing that you said earlier. Obviously, if there is a major deviation to the CAD model and it's not a critical regulation, that's something you still want to account for.
Because it is in the regs. There's
So if
similarity.
there's a hole like somewhere that's not supposed to be, you shouldn't just
Yeah.
Yeah, so if it just happens to skirt by the regulations, but it still is a significant deviation from the CAD model, that's something you want to change. But if it's a minor deviation, then I don't really see the point, as long as you cover it when you're finishing.
Yeah.
And it's close to the CAD model.
What
That's
would
the
a
key bit.
minor deviation versus a major deviation look like?
Maybe the height of the side pod from the track floor is 25.2 mil versus the 25 mil of the CAD model.
Okay.
Something like that.
Right.
I would say is a minor deviation.
A real side note here. With your tech drawings, a very common mistake that we see all the time is a lot of teams go to unreasonable dimensions for their car, 0.98, which realistically is not possible. So what teams, I guess we were guilty of this when we were competing, some just slip away, is really try and get 132 mils and have your tolerances to be quite to really actually be tolerances and really account for your manufacturing process.
I think that's actually a very insightful point in terms of just mentioning tolerances again. We went on a bit of a tangent in the Hydron interview. I don't know, Alex, if you remember, about tolerances.
Yeah.
But I suppose, Ethan, you were a CAD draftsman, or just a draftsman. Anyway, you made technical drawings, I think. And so when you're looking at a dimension, it's like 20.98 with a tolerance of half a millimeter. Isn't that 0.98 just completely meaningless when it comes to the tolerance? Because you've got such a high tolerance. Why not just say 21 millimeters? Is that what you're trying to say?
Yeah.
Yeah. Would you feel like on drawings that would just be, I don't know, infuriating for you to see, but also point loss worthy, I suppose?
Depends how you look at it. For my sorry,
Try again.
my voice isn't like me. Depends how you look at it. For us in mining, with the machinery we're working with, we had to be absolutely sure that we had the correct tolerancing. So
tolerancing is one of those things that's quite unintuitive. And again, sorry, is it intuitive? Stop and take a breath.
I would just say it's something that's hard to test, really, tolerancing. If you're collaborating with a manufacturer, they usually specify a tolerance they give you. Generally, it falls within the tolerance that they give you. But in terms of if you were to test the tolerance of your car body, that's something you if you have a time, I guess you could do a statistical analysis on in terms of what the actual tolerance is based on your own CNC machine.
But that would also mean repeat
Yep.
Manufacturers and all that kind of stuff. Yeah. So collaborate with someone about tolerances. Was there anything else anyone else had to add? Final call for testing opinions.
Do it.
Do it.
Do
Yes.
a lot of it.
And follow the scorecard.
I think
And check your cars.
a big thing is testing, for us anyway, represented the largest portion of our engineering design process. You should spend a lot of time testing.
I think you should never feel like you don't know what you need to change about your car, or at least know how you can find what you need to change. You shouldn't be sitting down in front of Fusion and going, I have no idea what to change to make this car better.
There's always something you can improve.
And the way that you inform that improvement is through testing. Okay.
Yeah.
Cool. I think that's it. Thank you very much, everyone, for joining us. Alex, Aarav, Ethan, and Feifei.
Thank you.
Thank you all for coming on. And thank you to all of the listeners for sticking with us for this long. We'll see you again soon.